Hello, and welcome back to My Idea Way. I'm Hayden. And the central question that I want to start on for today's episode sounds super simple. Who gets to build the future? And I don't mean who gets to use it or who gets to write think pieces of it after it is already the present. I mean, who actually participates in making the future? Who has the tools, who has the leverage, who gets let into the room. And on the flip side of that, whose potential just kind of goes away because nobody built a system that could recognize it. The person for this episode is Lynn Conway, computer scientist, electrical engineer, one of the most important people in the history of how computer chips get designed. There's, honestly though, a super good chance that you haven't heard anything about her. And that is part of why I picked her, because a ton of people whose entire careers ran on systems that she built are way more famous than she is. And by the end of this episode, I think you'll see why that happened and how it wasn't just some sort of mistake. Quick version here first. Conway worked on advanced computer architecture at IBM in the 60s. Later, at Xerox PARC, she and a Caltech professor named Carver Mead came up with a new way of designing what's called VLSI, very large-scale integrated circuits, which is just a term for chips that have a massive number of transistors packed into them. And what their approach to VLSI did over time was take chip design out of the hands of a small congregation of specialists inside giant semiconductor companies and make it something that a university class could teach. Students could do it, and small teams could do it too. Before we get into it, some of this episode gets super technical with the idea of VLSI or these things that you might not completely understand. But the actual idea underneath isn't chips. It's a distinction that I think I discovered for myself after I started reading about Conway. Some innovators build a great product. Other people build the process that lets 1,000 future products exist. One person might, say, invent a machine, but another person creates the language that lets more people invent machines. And those two contributions are completely different, even though famous people are often only the machine builders. The second kind of person is super hard to see because it doesn't produce an object. It produces everything around the object. The tools, the education, the standards, the stuff that becomes normal to it. And in that becoming normal, it becomes forgotten who really made that happen, you know? Conway didn't design the chips. She redesigned designing. And her redesigning of designing changed who could do it. To understand why that matters, you have to kind of picture computing before the modern setup existed. Today, the whole industry is layers. Some kid could learn to code on a laptop. A startup rents a bunch of computing through the cloud. One team might build processors, and a different team would build operating systems, and someone else builds apps on top of both of those. And nobody needs to understand every transistor within a chip to participate in it. The layers are super separate, and that separation is probably one of the most powerful parts about the entire chip industry. Chip design in the early 70s was nothing like that. Design was sort of tangled up with manufacturing in a sort of suffocating way. To design circuits, you pretty much needed deep knowledge of the specific fabrication process of circuits at a specific company. And again, every manufacturer had their own specific rules for how to make their chips. So the knowledge on how to make these chips lived inside big companies with expensive factories, and there was a logic to it, right? Chips were complicated, and fabrication cost a fortune, and mistakes were crazy, or rather not crazy, sorry. Mistakes would lead to massive issues within the chain. But the result of everything they tried to do to curb this was a bottleneck. You could be an amazingly smart computer scientist who had a real idea for a new processor and have literally no path to ever making it actually physical. The field had plenty of geniuses, it had imagination, but it didn't have access. And now I think that's the frame I want to carry this whole episode through, because everything else grows out of it in a way. A field can look like it has a talent shortage when what it actually has is an access problem. The people exist, the pathway to innovation does. When we see a small group succeeding in some field, our instinct is to presume that the people in that group are the only people who are capable of doing the work. But sometimes the system itself decided way upstream of the actual people doing the work who would be capable in the first place. Think about maybe a sport where the only kids who are able to make it are the ones whose families could coach them privately for a decade or start them when they were 4 years old. The kids who made it are really good, but the talent pool was sort of filtered out before anyone had a real chance. Or maybe a company where the big high visibility products always go to the people who already have relationships with executives. Those people get experience. The experience makes them look qualified for the next big thing, and it's sort of a loop. Opportunity makes more opportunity. Someone gets expected to succeed, and then they get resources that make them succeeding more likely. Someone else might get overlooked, and now they can pretty much never accumulate the sort of track record that would actually make them able to get out of that loop of overlooking. Conway's life, I think, shows both halves of the spectrum, which I think is what makes her such a good topic for a podcast. She built a system that opened a technical field of thousands of people, and she also got to experience what it's like when an institution throws away the talent it already has. Well, I think you gotta understand her story first to really get this stuff. She was born in New York in 1938. Physics at MIT, engineering degrees at Columbia, and in 1964, she joins IBM Research on this product called Advanced Computing Systems, which was an attempt to build a super high-performance computer. Her contribution there is worth talking about, I think, because her idea is really interesting. She worked on something called dynamic instruction scheduling. And the problem it solves is that a program is a list of instructions, but the instructions don't all actually need to happen in the exact order that they're written in. Some are just sitting there waiting on data to be collected, and others can happen in the background, like immediately. If the processor rigidly finishes every single instruction before starting the next one, it wastes a ton of time. Dynamic scheduling lets the machine look at the pile of rules and instructions that it has and figure out what actually depends on what, and then run things in a better order and having the same final result just in less time. That processor that she built is in your phone right now, running descendants of that idea of dynamic instruction scheduling. I kept thinking about dynamics schedule structuring while I was researching this because I think the idea behind it is bigger than it looks like. A dumb system processes work in the order that it shows up, even when that order makes no sense. A smarter system sees the dependencies inside of that order. The written sequence would say everything waits in line, but the actual structure says that half of this stuff could move right now. And I think you can see that everywhere. For example, teams, whether it be a sports team or a team in a job, sit around often waiting on one person because information or authority, or maybe they're a captain, put it on sports terms, are all concentrated in the same person. So say, I think the easiest way for me to explain this is lacrosse. Say you have a defensive captain, and he's the only one who has the authority to change the defensive set. But he also is the only person who knows all of the defensive sets. So if that dude's late, or if that dude's tired, or grabbing a sip of water, nobody can move without him telling you exactly what to do. The order isn't really the necessary order. Most of the innovation is available to happen when somebody notices that sort of gap in the order. So, Conway, she's doing frontier work inside one of the most powerful tech companies on the planet. And in 1968, after she told IBM she planned to undergo a gender transition, they fired her. She lost her job, her professional identity, the entire career she'd spent years building. She had to start from pretty much zero under a new identity, and then spend the next several decades carrying that fear that if anyone found out, she could lose it all a second time. IBM apologized in 2022, which is 52 years later. I want to be careful with this next part of her story, because I think there's a version of the story where the firing is like a plot device or something. Like, think of it as the obstacle that forged her or whatever. No, it was discrimination. A company had a brilliant engineer working at the edge of computing and chose to get rid of her. The loss was hers, obviously, but most of all. But I do think it's worth sitting with what IBM lost, because I think this is kind of the part that institutions never really think about. When a company pushes someone out, it doesn't just hurt that person. It deletes every single future contribution that person would have made there. Ideas that the company will never know it lost. Products that won't be able to get built there. People who won't get mentored there. You can't really count the value that really walks out the door when you fire someone. And I think that's why companies keep doing it, because you can never really measure the cost. Like, you can't put it in a quarterly report or something, you know? This is also why I think I've stopped thinking of inclusion, or like, I guess people call it like DEI or whatever, as a sort of separate moral category that sits next to the real technical work. I think it changes what technical work can become. And I think there's a version of the cost that might matter more. A person who has to hide part of themselves to be allowed to stay somewhere is always running a big background process in the back of their head. Will I be exposed? Can I push back on this without becoming about people like me? Do I need to be more perfect than everyone else here to be safe? And someone doing that math all day can't give their whole mind to the actual problem. And the organization looks at that person and calls it something like a confidence issue. It's not a confidence issue. It's the company making someone run a background task that takes up 10-20% of their efficiency all day, and the environment is the one making that happen, forcing that to happen even. Anyways, Conway rebuilt. She worked as a programmer, became a computer architect at Memorex, all while keeping her history completely private, because disclosing it could have ended everything again. And in 1973, she gets recruited to Xerox PARC. If you know computing history at all, PARC is pretty much a holy company. Graphical interfaces, networking, laser printing, big chunks of personal computer as a concept. And most of it traces back to that one lab. But I think there's one detail about PARC that matters for her specifically. Conway came into chip design without having spent her whole career soaking in the entire traditional semiconductor, transistor, everyone has to know every single part of this chip fabrication process, design culture. And I think to some that could be seen as a weakness, but in practice, it was able to be the thing that made the breakthrough that she made possible. And if you've been listening to the show for a while, this is sort of the same Chouinard outsider advantage pattern all over again. People who grow up inside of a system stop being able to tell which parts of that system are physics, things that need to happen, laws of the land, and which parts are just habits that sort of came from the start that aren't really necessary anymore. They know the rules so well that the rules just like appear natural to them. The outsider gets to ask the questions that the experts stopped asking. Why is this so complicated? Why is this knowledge chained to one specific factory? Why can't there be a cleaner layer between the design and the manufacturing? And I mean, to be fair, sometimes those questions are naive and really just naive, but sometimes they're able to expose something that was hidden by the rules that everyone else confused with necessity. That's pretty much what the Meade-Conway approach did. Transistor counts were exploding, and the old ways of designing chips couldn't be stretched up to match the amount of transistors that they needed. So they built abstractions. They were pretty much ways for designers to think about circuits at a higher level instead of having to think about the manufacturing details. One piece of this was scalable design rules, where instead of designers having to specify literally every dimension for one particular fabrication process, you could use simplified proportional rules that would survive at the base level as the manufacturing technology would change to support the higher transistor counts. Conway wrote that textbook. It's called Introduction to VLSI Systems, and it was distributed massively through universities. Let me stay on this idea of abstraction for a minute, because I think it's one of the most powerful ideas in all of tech, and people barely talk about it as an idea of itself. It's more just like a given in a lot of cases. Abstraction is how we handle complexity without holding all of it in our heads at the same time. When you drive a car, say, you're not personally managing fuel injection or ignition timing. You have a wheel and 2 or 3 pedals. The interface hides an enormous machine behind it, controlling a bunch of computer-controlled factors. Well, you're doing the only control that you need to do. Same with, say, like tapping an icon on your phone. You're not managing the radio waves that are going to your phone or allocating memory to each specific app. The complexity behind it is all still there, but it's pushed down to a different level where somebody or something else handles it. That's pretty much what the VLSI methodology did for chips. The physics behind the chips didn't go away. The fabrication constraints behind them that were governing what they could be made before were still real and still mattered, but the link between designing that chip and understanding one specific company's process of making a chip was sort of loosened up, per se. A student didn't need to spend 5 years inside of a semiconductor company before being allowed to think seriously about chip architecture, or really just chip architecture at that one single company, not to anything else. That, to me, is really the measure of what a great abstraction really is. It doesn't speed up people who are inside the company. It changes who can get into the company at all, or rather not the company, the field that the abstraction is based in. I think there's a leadership lesson in here as well. When someone struggles with a system, the reflex of people, I think, is just to always blame the person who's struggling. Maybe they're not technical enough. Maybe they need more experience. But sometimes, and I mean sometimes, the person is fine and the interface itself is the problem. Think about joining a company where every important decision depends on knowledge that isn't written down. The veterans know the knowledge, and therefore they look intuitive. They know who to ask questions of. They know which rules really matter and which rules don't. They know what phrases mean in, meanings or something like that. But the new person would look slow. Now, they don't look slow because they lack judgment or because they don't have information, but because their ability to judge fast gets built out of experience within the company, or rather just context of knowing things, and nobody ever gave them that context. The organization sort of confuses their history with intelligence. The Conway move here is to ask a different question. How much of the difficulty here is because of the actual work, and how much is just residue from having a badly designed system? Because those are completely different things. A hard math problem is super demanding. An unreadable textbook is an extra level of difficulty that is stacked on top of that for no reason. The first kind of problem, a hard math problem or something like that, produces growth in the student. The second kind just filters out people who haven't read stuff like it before, if that makes sense, because someone who's experienced in the subject would be able to read between the lines and understand what's there. Someone who can't would just get kicked out. A good system at its core strips out that accidental difficulty without taking away from the difficulty of the problem in and of itself. Chip design was still super hard after Conway made her VLSI system, but it stopped being pointlessly closed off to new people who wanted to get into it. Now, here, I think, is where she separates from pretty much everyone else who's ever invented a method, I guess. She understood that a method only matters if people can learn it. In 1978, she went and taught a VLSI course at MIT herself, and she gave students the opportunity to design real systems using the new approach. And the teaching wasn't some, like, I think as a lot of these things are, they're very downstream of the activity. They happen after the innovation was done. The teaching for Conway was part of the innovation. The method had to be teachable because a technology only its inventor can use has no point. And a framework that thousands of people can use has a massive effect. It pretty much compounds to the entire industry. You can see this pattern across half of her story at this point, I think. Or, sorry, half of the entire One Idea Away story at this point. Edmondson didn't fix one team's communication problem. She gave every organization a language for why people go silent within companies. Clear didn't hand anyone a rulebook for having perfect habits. He gave people a way to think about systems and identity as a whole. The ideas that are actually able to change things are pretty much always the ones that can compress experience into a way of thinking that can travel across different people. I believe there are brilliant people out there anywhere who can solve anything and end up transferring nothing, if that makes sense. All of their value is only to them. But teaching really wasn't the only bottleneck in the chip design area. And I think this next part is probably the most important business idea in our whole story. Students could now design chips. I mean, cool, but a design isn't a chip. Fabricating a chip means manufacturing, and manufacturing a separate, new, novel chip for every single student project would be insanely expensive. So Conway helped build a system where a bunch of independent designs from different groups would get combined onto shared chip products. Everyone submits and the designs get sort of combined together. The costs, therefore, are split between these different projects, and the finished chips go back out to each designer and can be tested to understand each part of the chip, what works, what doesn't. That work led to a service called MOSIS, which gave universities and, I guess, small companies too, access to semiconductor fabrication at a small scale. And it helped create what became the fabless model, which is the split between companies that design chips and companies that manufacture them, which is now actually how the entire semiconductor industry works at its core. When you hear of, say, NVIDIA designing chips that TSMC manufactures, you're hearing about a descendant of Conway's logic. Think about what that closed. Before, a student could produce a design on paper and never really test if it worked. After the design met reality, reality would expose the mistakes in the paper, and then those mistakes can make better engineers as students. Design it, build it, see what happens, learn, design again, and you loop it. And that loop is amazing, I think. It's sort of the same void point from 2 episodes showing up in education. People don't get great from receiving already done information. They get great from being inside this sort of feedback loop. And if you're locked out of real projects until you already have 5-10 years of experience within a specific company, you can never build the experience that would unlock the real products in the future. And I think that trap is pretty much everywhere today when you like understand it. Companies that want leadership experience but never let anyone new lead. Creative industries that only fund proven work, which means they only ever really get to work that's already funded, if that makes sense. The system demands having evidence of something actually working. Well, they control access to the only way people can actually get evidence of something working. I don't know, sort of a wordy explanation. Conway pretty much broke that negative loop for an entire field. Universities changed from places where you could study chips that other people had made to places where you were able to make chips yourself. And that's, to use Naval's sense, that's leverage. But I think it's a kind of leverage that we haven't really covered in this podcast before. It's not code that runs in the background. It's not capital that generates you money in the background. It's not media that develops influence. It's infrastructure. She changed the entire pathway, and once that pathway that she created existed, thousands of people moved through it without her having to do anything for any individual one of them. And the reason you've never heard her name is baked right into the nature of her contribution. No chip ships with a label saying Lynn Conway made this possible. Infrastructure is invisible pretty much. You only notice a bridge when it collapses. When it carries traffic every day, you don't think about it. Good infrastructure creates the sort of feeling that the possibility was always there. It wasn't always there. Someone removed a bottleneck, and then everyone forgot what it was like before that existed. And I actually think that this reframes what strong leadership actually is. A weak leader becomes the most important person in every process. Everything has to go under their approval. They have to know about it. They have to put their energy into it. And the whole thing can look successful because the leader constantly has to swoop in to rescue it. A strong leader builds capacity and builds a team that can work past themselves. More people who have the context to solve problems, more people who can decide, more people with access to the tools that actually need to get work done. The leader is less central to every individual action and really needs to be more important to the entire system overall. But I think it's important to note what that requires. It requires a weird relationship with having credit. If what you really want is to be recognized as the source of every important idea, you will start building dependence. You'll want to be needed. Whereas if what you want is for the group to be able to do more and to actually make a difference, you'll transfer the knowledge you have. You'll build interfaces and tools that people can use in place of you so that they can work more efficiently. And the better you do it, the more your own fingerprints on the projects disappear. The system just works because that's what it's designed to do. So people assume that it's always worked like that. It's just like how it works. I mean, the word works like 4 times. It's just how it is naturally, which is exactly why I think history remembers the product people and forgets the infrastructure people. Product has a day that it came out and a name and a person on the stage announcing it. And infrastructure develops across multiple institutions in some cases multiple fields, and populates through courses and through documents over the years. And there's no announcement date for a new infrastructure dropping, you know? We as a society want to honor individual heroes, but what actually happens is more in the background. It's in the infrastructure, which I should say is a warning that applies directly to this episode. Conway didn't do this alone. Carver Mead was a massive partner to her. Students also tested and extended all of her learning. Universities adopted her courses. DARPA funded her infrastructure. Moses outgrew any single person that started it at its core. And this show is literally structured as one thinker per episode. So I gotta be honest about the limits of my own format here. The person is a lens into the system, not the system itself. What makes Conway's contribution real isn't that she invented every single piece of it. It's that she saw how the pieces connected. Method of designing chips, education, tools, access to manufacturing. Each one helps the other. And seeing that anatomy is its own skill. And I think it's probably the rarest one we've gone over so far. A company can have amazing engineers, a bunch of money, good tech, and still fail because no one's looking at how those things interact. Where information doesn't travel well, where one department is grinding on a problem that another department could solve super easily, where a great idea dies out or doesn't get to the next area because there was never a path from that idea to making it real. You don't have to build every component individually to be successful. You have to figure out how the components work with each other. Conway did that across an entire field of chips and incorporated labs, universities, the government. And later, she ran strategic computing work at DARPA and became a professor and an associate dean at Michigan. And it was precisely her moving between worlds that let her see those gaps. Universities had ideas, but no manufacturing. Industry had manufacturing and no, what's the word I'm looking for? No leeway for academic weird ideas. The bottleneck for chips wasn't in really any one of those worlds. It was between them. Okay, late in her life, around 2000, Conway started telling her own story publicly. The history of her complicated past that she had hidden for 30 years because she pretty much had to. And she named in here a pattern that I thought was super interesting when I was researching. She called it the Conway effect. People who aren't expected to innovate are more likely to get written out of the story afterwards. I think that's a super interesting lens on bias because it's so much different than just regular bias. History doesn't really record exactly what happened. It records what people were prepared to believe happened, like what wasn't surprising. If you already fit the idea of an inventor, your contributions get noticed easily. You get quoted in a textbook, you get invited to things, your version of the story gets repeated. And every round of that recognition in public creates more opportunities that give you more recognition in the end. Someone else might contribute just as much to the whole, but they don't fit the image of an inventor, and therefore their work gets sort of put under a different title. It's support, it's collaboration, it's teaching, it's testing or something like that. And the thing that makes this so hard to fight is that there's no bad person behind any of it. It's run pretty much entirely on small assumptions. The person leading the meeting is assumed societally to have made the idea. The person with the impressive title is the public face of the idea. Then, decades later, historians go look at the record of what actually happened, and the famous person has interviews and rewards and profiles, and the overlooked person who actually did much of it, or at least equal, has no evidence. And that unequal recognition starts to seem like it was the historical truth of what happened. Visibility creates more visibility. The system, in this case, the system of history, remembers who it wanted to remember, or I guess expected to remember. This is kind of Boyd's orientation problem running at the level of the system of history. If you think about it, the mental model filters information. Then the filtered information gets held up as proof the model is right all along. We promote the people with the impressive title, the public face like this, because people like this perform best. Okay, or people like this were the ones handed the assignments and the sponsorship and the leeway that performance requires. The system manufactures the evidence or the publicity or the quotes in textbooks that it later uses to justify that being true. Feynman said, "You're the easiest person to fool." An institution at its core is really a bunch of people fooling themselves all together. Conway died in 2024. She was 86. Most of her recognition came decades after her work, including the 2020 IBM apology, 52 years late. And an apology that late can't give back the career that she might have had. What it can do is make you nervous about right now. What are we failing to see at this moment? Which of our current decisions is going to look embarrassingly wrong in 50 years? Who around us is hiding something just to be allowed to stay? Because people in the future are going to find our blind spots just like we found IBM's in hindsight in 1968. And I don't think the point is to be superior to the past. The point is to be careful about our own certainty. So, here's some questions that I've been carrying around since I researched her. Where is intelligence getting wasted around me because the interface is bad? Where does a field or a class or a company look exclusive when really its knowledge just was never accessible to those outside the company, and therefore they're missing out on a bunch of talent? Where does some process I'm part of demand evidence from people while controlling the path to get evidence, and therefore, again, putting in a bad loop that makes it impossible to advance? And then I have a personal one. When I build something that works, am I making people depend on me? Like perhaps in a group project, like I do a bunch of the work, and it becomes a great project, but I don't actually help my classmates build something without me. So like, am I making people depend on me by not knowing how to do things, or am I expanding what they can do on their own, right? Like without me? Because I think some people will build the future by making a super cool machine or a new chip, a new computer. But other people will change it by deciding who gets to build things at all. I mean, Conway did both. Her architecture work at IBM was really cool, and her VLSI revolution was amazing. But I think the deeper thing is pretty much always going to be the second one. She showed that the most powerful innovation is probably never in the object. It's about building the road or the bridge. I think a bridge is a better analogy because it's over water. Like there's no other way to pass over it than over this bridge. That everyone after you will drive on without ever knowing who built it exactly. Thanks for listening to My Idea Way. I'll see you next time.